Hello, I'm Colonel Worth, and I have been cooperating with Colonel Potter on the possibility of traveling to planet Aldrin, which orbits around the star Borman. And so, uh, in this presentation, we will be discussing the trajectory of the planet Aldrin, the hazards and procedures of travel, as well as the cost efficiency of travel. And so initially I will be discussing the position and the trajectory of the planet's orbit. So to determine the planet's orbit, first we used Newton's second law uh, in accordance to gravity here, and through this we were able to determine the planet's position functions or regarding the x-axis, the y-axis, and the z-axis. And so we determined that these equations actually represent how the planet travels, and we will be able to use this data to determine the best path for our rocket to travel in order to land on the planet safely. And so in this equation, the mass of the planet is represented by the lowercase m. This is the mass of the star Borman, and this is the gravitational constant, which is 6.670 times 10 to the negative 11. And so, as we began to calculate in using a variety of different initial values, we discovered that in one set, that energy wasn't precisely conserved. And to calculate energy, we use this equation here, which is also in relation to the position of the planet. And so we know from physics that energy must always be conserved. And so with this data and this determination, we were able to determine that our data may not be 100% valid at all points. And now I pass it off to Colonel Potter to discuss more about the trajectory.
Okay, so we can like map out our trajectory using this function here. We have the sum squared error here, and we use this to find E and D. Those are constants that will determine the whether the orbit is kind of narrower or more circular, or kind of more elliptical. And Kepler's second law shows it says that pretty much at any point in the planet's orbit, at any time increment, and if you draw an imaginary line from the sun to the planet, it will cover like the same area, and that kind of maps out for us the path of the planet, and we can use these factors to parameterize the orbit and model it. Now I pass it over to Colonel Worth for number 3.
So when determining the actual precautions and requirements for travel, we looked at the other forces that would be enacting upon the rocket, such as the gravitational pull of our sun, which is determined by this function here, and as well the gravitational pull of the star Borman is also determined by this equation here. And from there, we were able to determine exactly how the rocket's travel would be affected by these two large bodies of mass. And when determining how the rocket would act as it approaches the star Borman, we must consider whether the vector field will be conservative or not. And a conservative vector field is a vector field whose line integral depends only on the endpoint of the curve. And so using this, we were also able to determine the work, because we could determine the distance using the star Borman as our origin and placing our sun at point 10.1, comma 9.8, 8.7, and these coordinates are all in light years, and the conversion from light years to meters is 1 light year equals 9.461 times 10 to the 15th meters. And so with that, we were able to determine the length of travel as well as the force and how it would act on the rocket, and then to determine the safety hazards when the rocket approaches the sun too closely or the star. The possibility of radiation poisoning increases, and so each planet has a protective shell around it for radiation, and to determine that shell and whether our rocket will be able to remain in that shell, we use the equation here, which is relies on the position of the planets. And so to discuss the cost efficiency of the rocket, I pass it off to Colonel Potter.
Okay, so for the rocket, we want to use a multi-stage rocket, which pretty much allows the rocket to be as cost efficient, to use the least fuel as possible, and allow for the quickest trip. And this occurs by when the fuel is used up in part of the rocket can kind of get rid of that part of the shell. And so it kind of sheds the outer layer when the fuel is used up from that part, which ultimately just maximizes efficiency, uses less fuel, minimizes cost. And so to minimize the total mass of the rocket, we're given a velocity function that it has to reach, and if we derive that, we'll find the force, and we can use that to in the force function, mass times acceleration, to determine the mass of the rocket, and these to find the best trip. So this is our representation of the trip to the planet and what we found from that.